Our special product patterns can also help us solve regular multiplication problems using mental math. Now, I'm going to actually write down the steps here, but this is something you could kind of think of in your head. Okay, so just kind of see how this works. It says use mental math to find the product. 19 times 21. Probably not something we can do in our head, but looking at both of these numbers, I realize that both of them are very close to 20. In fact, I can rewrite 19 as 20 minus 1. And I could rewrite 21 as 20 plus 1. Look down here. Same first term, same second term, adding and subtracting. Okay, and again, multiplication in any order, so it's okay that we have subtracting and then adding. So what that means is we could do a squared minus b squared. This is the sum and difference pattern. So I could go 20 squared minus 1 squared. Well, 20 squared is 400 minus 1 squared, which is 1. So that actually works out to be 399. Not something in my head I would probably think of, 19 times 21 being 399, but by setting up 20 minus 1 times 20 plus 1 and using our sum and difference pattern, we could easily see it's 399. Let's look at another example. 38 squared. Again, not something I can do in my head, but I do know that 38 is pretty close to 40. In fact, it's 40 minus 2. So if I rewrite 38 as 40 minus 2 squared, I have this special pattern right here on the bottom. Since it's minus, we can go a squared minus 2ab plus b squared. So our first term squared, 40 squared, minus 2 times our first term, 40, times our second term, 2. Notice I'm not going keep, change. I'm taking into account that this is minus from this pattern. Okay, this is going to be a minus 2 times 40 times 2, plus our last term squared, 2 squared. Now, 40 squared is 1600, minus 2 times 40, which is 80, times 2, which is 160, plus 4. 1600 minus 160 is 1440. Well, plus 4, 1444. So again, just kind of something else we could maybe do in our heads just by using our special product patterns. Okay, so we can use these product patterns for mental math. Let's look at one more example. This is a little different. It says 2 green snapdragons, each with 1 yellow gene and 1 blue gene, are crossed. Each parent passes along only 1 gene for color to its offspring. Sorry, this is supposed to be color. Show how the square of a binomial can be used to model the Punnett square. So remember the Punnett square. Let's see if I can draw a straight line here. Basically what's happening, remember from your science class, is that one parent is giving a yellow and a blue gene. So they're going to give a yellow and a blue gene. And the other parent is also giving a yellow and a blue gene. Excuse me for 1 second. Okay, so sorry about that. But so each parent is giving 1 yellow and 1 blue gene to their offspring. So we could either have a yellow and a yellow and a blue, yellow and blue, or blue and blue. And of course, depending on which one of these is the dominant color, would depend what color they are. But show how the square of a binomial can be used to model the Punnett square. Each parent is going to have a yellow plus a blue gene. So if you're thinking about in terms of each offspring, they're getting one of the genes from the mother and one of the genes from the father, or vice versa, however it is. So what we can do is say half, that's what the 0.5 is, Half is coming from one parent, half is coming from the other parent, basically. That's what this side represents. And this side represents also the same thing. That's how we can square it. Because if we wanted to figure this out, we could go 0.5 y plus 0.5 times b, and then times it by this right here, which would be the same thing from another parent. And we can just write that by squaring it. Now, our special product pattern right here, I'm going to slide it down, says that if you have one term plus another term squared, all we have to do is take the first term and square it, plus 2 times the first term times the last term, plus the last term squared. So my first term is 0.5 y, so we're going to square that, plus 2 times our first term, 0.5 y, times our last term, 0.5, not forgetting our b, plus our last term squared, 0.5 b squared. Okay? And that's just using this pattern right here. So now when we simplify this, 0.5 y squared becomes 0.25 y squared plus 2 times a half is a half, 0.5 y b plus 0.5 b squared is 0.25 b squared. So what does that mean? This means that if we look at this, 25%, 0.25 will be yellow, 25% over here will be blue. And I know I said earlier depend which is dominant. Well, they're green snapdragons. If we combine yellow and blue, we get green. So that means 50% of the snapdragons will be green. Okay. So by using the square of a binomial, we can show this chart that the percentage of each one. 1/4 the chart, 25% is yellow. 1/4 the chart, 25% is blue. And then we have 2 squares here, so 50% are green. So the square of a binomial can also show us how the information on a Punnett square. So with all of these, ladies and gentlemen, remember, focus on the special product patterns, and hopefully can make the math a little bit simpler for you.